how I will penalize it with a square. When h is 0, this is 0, and I have the same solution of this problem. Because this is 0, the solution, this will be the minimum of this, is the minimum of this, because this constraint is fulfilled. What did you do with this? You remove one constraint, you remove one variable. No, you change your problem. And what did you add? You add a parameter that is called penalty parameter, rho. Probably you have worked in penalty methods. So people who are working in penalty methods, they do this. And this is penalty parameter. You want to stabilize the divergence of U in Stokes. You penalize it with this, and you don't have any more the pressure. And then the optimality is you minimize this. These are Carrot's finite condition. This is unconstrained optimization. What do we have? Gradient of the function equal to 0. Gradient of the function plus rho and gradient of h 2 times h times the gradient of h equal to 0. Okay. This is one possibility. Let's see another possibility is to do linear penalization problem. So what you do is the same problem as you had, but you penalize with a parameter nu k with h. This problem is equivalent to this problem because when theta is equal to 0, this is 0, and minimizing the function is the same as minimizing this function. So it's equivalent. This is a constraint optimization problem. So if it's a constraint optimization problem, the Carrot's-Kanitta condition is what you have to do to have the optimality condition. So you do the gradient of f, the gradient of h, you have it here. This nu and nu k, you add them. Nu is an unknown, nu k is a parameter, and you add the constraint. And you again has a nonlinear equations that you have maybe to use Newton or whatever. You have to solve. Okay. What you can do also is doing a quadratic penalization of this linear penalization. So what I will do now is, okay, I have this problem, but now I'm going to add a penalty, quadratic penalization. And now here people are not calling it anymore penalty method. Yet rho is called penalty method, but this method is the augmented Lagrangian. This is the penalty method. Okay, but rho still calls penalty parameter in augmented Lagrangian. And this is not consistent. And this typically is consistent. So what you do here is you do the gradient. So now here you have an unconstrained optimization problem, and you will have the gradient of f nu k plus 2 times rho h times the gradient of h. Here you also have the gradient of h. I put it here. Okay. So see, this is the quadratic linear programming problem. And now we call it QLP. This LP, this B, and this QP. So now I'm going to present the regularization of the base problem. Again, another regularization. You see, regularization comes many times in numerics. So we have the function, the cost, the constraint, and now I penalize quadratically. But I didn't remove the constraint. Here I have removed the constraint. And here I didn't. Okay, are different. So you still have the constraint. Okay, so let's see how it works. When you have your problem B, you have the unknowns theta and nu. When you go to the unconstrained to the quadratic penalization, then you remove nu. Here you don't have any more nu. And then when you pass from here to here, you add this term here, rho, with the quadratic term. Okay. Here, you add the constraint. You have the constraint still, but you have nu and nu k. Okay. So again, from here to here, you add nu k as a parameter. From here to here, you have add as a parameter nu k also. So moving from the left to the right is deleting the parameter nu, and moving from up to down is deleting the parameter nu k. Okay. So you have this square here. So going from here to here is adding nu k, and going from here to here it's eliminating nu. So in fact, if you go here, you have eliminated one variable. If you go here, you have added one. But if you go here and then to the right, you have added and eliminated. So you are in the same position as you were. Okay. So this is a little the intuition of why you have to. It's better to solve, or you didn't change your problem when you have in sense of constraint unknowns when you move from B to QLP. Yeah, you have eliminated but then added, or you have added and then eliminated. So the optimality conditions for this regularization-based problem, regularized-based problem is gradient of f times 2 times this, and you see the different. Sorry, this term is this one, and 2 times this term is this one, and also the constraint. And this is a system of equation. Okay. So you see this regularization problem is when NUCA, the way you pass from here to here is you have deleted nu and you have added nu k. So if nu k is nu star, the solution, this way of solving the problems with nu k with data are the same as the regularization of the base problem. Okay. And see, these optimality conditions, KKT or KKT here, are very similar to these ones, but which is the difference? Let's see what is the difference. You can see it or not? Not a lot. Here you have this term, and here you have this term. This is the original problem. So what you want to do is at each iteration trying to this part, make it similar to nu. So you will try to fulfill this at each iteration. You will try to, the new nu will be nu k plus rho h theta, because you want to have exactly the original problem. So this is how you will change your Lagrange multiplier. So remark, if nu, if at the next iteration you have nu k plus rho h theta equal to nu star, then the optimality conditions of this problem and this coincides with the ones of B. Okay. The algorithm. Which is the algorithm? Very easy, or not? So the algorithm will be, sometimes it's called primal dual, and is primal dual, but in some sense, yes, is first minimizing with respect to theta. Okay, so first you have the Lagrangian, but the regularized Lagrangian, and you solve theta. This is an unconstrained optimization problem. What do we do? What do we use here? What can we use here? Stochastic gradient, Newton, quasi-Newton. But remember, we are in an augmented Lagrangian, so what we like to do sometimes, maybe people are using Newton sometimes, but here what we want to do is go fast. So maybe we will use a gradient descent for here. But you can use Newton if you want those. You solve this problem, and then you change your Lagrange multiplier. But here nu is known. Here it's only theta, the variables, and here the known is nu. So it's like for a Stokes problem, for example, here you only change theta. So you only change the velocity, and there you change the pressure. Okay, you will never do this in a Stokes problem because you have a quadratic problem and you do an inverse and you finish in one iteration a quadratic problem. But if it's to understand what we do, we separate the dual and the primal in one iteration, or we do many iterations in the primal, and then we do some iterations in the dual. So we alternate directions. Okay, this is how the algorithm works in the augmented Lagrangian. How many iterations do you use here? Do you end? You find the best theta? Sometimes you try, sometimes you don't. You just do some iterations and you get better f. Once you have theta, you go here, you update your lambda or your nu. You go here, you change theta. Okay. So this is the algorithm. Let's now understand it and have some insight of it. Imagine we have this problem. Okay, this is the original problem. Now we write the Lagrangian, and then we write the dual function. The Lagrangian, remember, it's just with this, and the dual function is minimization of the Lagrangian. Then the second derivative of the Lagrangian, which if you want to compute the dual, you have to solve this problem. Is this problem convex? If it's differentiable, it will depend on the second derivative of L. So we take the second derivative. It's not the second derivative only of f. Now you modify the second derivative of f. So it's like the Hessian, you modify it with the Hessian, with a parameter of the constraints. Okay. This is for the base problem. So sorry. This is for the sorry. This is the L for the base problem. Sorry. The modification is here. Now you add this term here. Then you have the Lagrangian. You add this term. Then you have the dual, and then you have to see the convexity of the dual. With the same term as before, and also this. But now you have an extra term. So it's like your Hessian that you had before, you add some terms. That depending on rho, then imagine that sometimes this is not definite positive. But depending on the rho you add, you can make them definite positive. And what does it mean? You convexify. What does it mean? That locally you convexify. So first thing, for the dual, the gradient, when we want to compute the dual, we have to solve this minimization problem, and the Hessian has been modified with some extra parameter. Okay, this is the message. The gradient of the dual function, let's see now the gradient of the, not the dual function, the gradient of the dual function. The gradient of the dual function is, we have the function, which is this one, minimization of L. Then theta is the solution of this problem. So theta will for sure fulfill the optimality conditions because this is an unconstrained optimization problem. So the gradient of all of this will be equal to 0. So the gradient of this plus 2 times nu, and here I should put nu and not nu k. Okay, is equal to 0. This is the gradient. Optimality conditions for this problem. If you obtain the optimal solution of theta and then you plug it inside, then you have the dual. The dual is obtaining the optimal theta and plug it in the cost. So you take the value, you put it here, you put it in H, and you put it here. It's just what I have been doing here. But now theta depends on nu. Depending on the nu you give me, I will have one theta or another. Then I take the derivative. The derivative of J is the derivative of this times the derivative of theta respect to nu, 2 times a derivative of H times the derivative of H respect to theta and the derivative of theta respect to nu. And I put lambda, but it's nu. Okay. And then this derivative. But this is 0 in the optimal value. So because of this. So the gradient of the dual is the constraint. The gradient of the dual is the constraint. Okay. Why is this useful? Look, since what we want to do is to maximize the gradient, remember the dual. Do you remember that the dual is a lower bound of the primal and you want to maximize it? Then if we take this iteration of the dual variables, the one that we have said here, the one that wanted to be similar this than this iteration of the dual, then this problem of maximizing just nu is the gradient algorithm. You see? Why? Because the derivative of g we have seen is the h. So nu here you don't have any more theta. Theta depends on nu. So nu k plus 1 is equal to nu k minus, here I should put a minus, rho, no, a plus, because you want to maximize, to h theta. So theta of nu, of course, of this solution. Right? So this iteration of updating the dual is the same as thinking that what you are doing is doing a gradient ascent method, or steepest ascent method for the dual. And rho can be interpreted as a line search. So the Lagrange, the penalty that we were saying before, which value I put in the penalty, how much I put in the penalty, in fact, is the same value, the same tau we have been seeing in the gradient methods. Let's go to lecture 3. Gradient method. Where is gradient method? Or it was in no, this one, lecture 1, I think. Yes. Where is gradient method? Here. You see? You remember tau, the line search? I put it in brown to make it all this. So rho is the line search for the dual. So we have an interpretation for it. So if we choose rho such that we maximize the dual step, we will increase the rate of convergence of the dual problem. So if you take rho or the penalty, because people always ask which penalty put. If you put a penalty very large, then you will converge fast with the dual. What does it mean to converge fast in the dual? It means that the constraint will be satisfied fast. Okay. So the Hessian of the dual is the gradient. Now I have spoken about the dual, the gradient of the dual, and now the Hessian of the dual. The Hessian of the dual you can compute by chain rule, and you will see that it's this function here. If rho goes to infinity, then this, not in infinity, but before, can be interpreted as 1 divided by, the only important term is this term, because this term doesn't matter. And then h with this h can be you put it in the right, and it's very similar to the identity. Okay. So we can approximate the expensive. Imagine you want to solve the dual. If you want to solve the dual with a Newton, instead of putting here rho, you will put here the Hessian of G, and do the inverse. So what you can interpret is that in fact you are like preconditioning your problem with identity, but 1 over rho with a parameter rho. Preconditioning, very bad preconditioning, very bad. Just with one parameter, but very fast. So with one parameter, you precondition your dual. Good. So if rho goes to infinity, then the Hessian of the primal, then it goes to infinity, the condition. But if you go to infinity, the dual, the condition goes to 1. What does it mean? It means that when the density, the penalty term is too large, you just take care of the dual. If it's too slow, you just care of the primal. Okay. So typically people, what they do, or it depends on the problem, you can start with a small value and you care a lot of the primal you want to minimize, depending on the complexity of the problem. And then you can start increasing, but you don't have to go to infinity. In penalty methods, you have to go to infinity. Here you don't. Here with rho equal to 10, or even you leave it with 1, you can convert. Okay. But it can be slow also. Slow in the sense of number of iterations, but every iteration is very fast. It's like explicit methods. Every iteration is very fast, but a lot of iterations. I don't have much time to explain it, but we have done it with Tony also in his graduate thesis. We can use acceleration methods, okay, that you don't have to do inverses. It's called Nesterov acceleration, and this, what you can do is to solve without doing inverses, going very fast. Okay, so people say explicit method, maybe it's true that you will have to do a lot of iterations, but all of them are very fast, and there are methods to accelerate a little, so much. Okay, so the good thing is you can deal with many data, many unknowns. That's what we want to do in machine learning. Finally, for the augmented Lagrangian, let's give an interpretation of this parameter rho. I put a very simple example, just to understand it. I made this example. I think it's clear. So imagine you have these three. I think this example probably you have solved it, all of you in the engineering courses. So you have 3 blocks here with a mass at each point. And here there is no mass, so just points. But you can do it also with masses and springs in between. So your internal energy should be equal to the work, external work. Okay. So, and K is a stiffness matrix, which is the addition of K's. Okay. And F are the forces that you apply at each point. F are in color in yellow. If you add this penalty term, if you regularize with this, then it's like if you're adding a row, you want a square. You regularize the constraint. You want that this point is fixed. Okay, so you regularize the constraint. Now it's like adding this term to the cost, but this term is very similar to this, to the internal energy. So in fact, you can add it and you put it here in the 1-1 term. Okay, so just you put it here. Then how you can interpret it in this sense? You can see it like a spring in this problem. And when rho goes to infinity, it's like a infinite rigid bar. So you have these 3 points, they want to move, you put forces, but you want that the point in the left is fixed. Okay, so this condition, to impose these conditions to be fixed, instead of putting a penalty equal to infinity, to put a very rigid bar, people are sometimes doing these kind of things. What you do is you put this spring. Then it's more smooth. Of course, you can start with a very large value, and the larger this value, the larger it's going to you are going to fix this constraint. And if it's very small, okay, you will do it, but it will take very much time. Okay, so there is this interpretation of the penalty method, the penalty parameter. So okay, augmented Lagrangian and interior point methods. Explain. Questions? It's too much for I understand. Okay, so a little more. I think more or less the general view, I hope you see it. You have constraint optimization and constraint optimization. We have algorithms here, gradient, Newton method, quasi-Newton. We have Carlos-Kanitaker, and we have gradient equal to 0, Carlos-Kanitaker here. We have augmented Lagrange and interior point methods. Some of them are implicit and expensive. Some of them are, you have a lot of iterations, but each iteration is cheap. Okay, so this is more or less the picture. I know there are a lot of things in there, but this is the picture. Okay. Let me end this constraint optimization problem with a very useful application, and probably most of you, or a lot of you, have worked on this, which are the adjoint methods, adjoint problems, which is a version that is not used in machine learning, but is used a lot in computational mechanics. So I think, since most of us come from this discipline, I think it's perfect to present it here, because it's what we use when we have PDE constraints optimization. So imagine you want to minimize something, and the constraint is the equilibrium equation, or the Navier-Stokes equation, or any PDE you want, which you know that you can solve it, but it's very expensive, very expensive. So you don't want to put it with Lagrange multipliers, or you don't want to use interior point methods, because already the constraint is extremely expensive. So what do we do? And this is called control problem, PDE constraint optimization, sometimes called PDE constraint optimization, or control, optimal control. You can see it also. Because you want to control some variables. So what you want to do is imagine this is the, for example, imagine this is the elasticity equation, and you want to change, for example, the Young modulus, or you want to change the viscosity in a problem, or you want to change, I don't know, anything. Okay, and you have the unknown here in the operator. And this is very useful, because you not only want to solve a Navier-Stokes problem, you want to solve a Navier-Stokes problem, for example, with, I don't know, how should be the shape of a cylinder. Anything you can ask of the problem, you put it here. Okay. The only thing that must happen in these problems, PDE constraint optimal and optimal control, is that the constraint, if you give me X, then I can solve the problem. So this constraint should be solvable. For example, if you give me viscosity, I can solve Navier-Stokes problem, or the Reynolds. If you give me the shape, I can solve the Navier-Stokes problem also. If you give me the Young modulus, I can solve elasticity. But you have to solve this problem. So this is a square matrix A, solvable. This is the only condition. But all of our applications or our PDEs must be solvable. Okay. So A, invertible. So what people do typically is they do a reduced cost function, okay, or reduced formulation of the problem. What does it mean? See, here you have X, Y as an unknowns, and I didn't put it, but in fact, what do we have if we have a constraint? What do we have if we have a constraint? What it appears in an optimization problem when we have a Lagrange multiplier. No, we put it always. So even if people solve this problem, sometimes we don't know that here there is a Lagrange multiplier also. Okay. So what people do is, okay, I'm not going to see this problem as two variables, as X and Y. I want to see it with just one variable, with X, my design variable, my Reynolds number, the shape of my cylinder. So Y can be always computed. Once you give me the shape of my cylinder, I will always give you the velocity, so I can always, for example, know the cost. Could be, for example, minimize the drag. Okay. So what do you do? I put it here in a vector form or matrix discrete form. Okay. Later, I leave it to you in the notes, but it's in the continuous form. So A times A minus 1 properties. Easy property. A times A minus 1 is equal to identity. do the derivative. You do the derivative of the a times a minus 1 plus a times the derivative of a minus 1 equal to 0, because the derivative here is 0. Then the derivative of a minus 1, you leave it in the right hand side, and all of this to the right hand side with a minus, and then you do the inverse of a, and you put it here. So if you want to do the derivative of the inverse, what you have to do is do the derivative of the matrix and multiply behind and before times a minus 1 with a minus. This is the derivative of a inverse. Sometimes it's not easy to know what is the derivative of the inverse of a matrix, but we need it. So what you want to do, now you see this problem with no constraints. What you want to do is to use a gradient method to update your unknown. So you want to have the gradient. What is the gradient? Partial derivative. The derivative of j respect to x times the derivative of j respect to y. So this other argument times the derivative of y respect to x. The derivative of y respect to x is the derivative of, since y is here, is the derivative of y respect to x of a minus 1 times b. b can depend on x, so also it's the derivative is a minus 1 times the derivative of b respect to x. So usually b does not depend on x, but I put it in general. Now I need the inverse of the derivative of the inverse. So I took this. Where I have the derivative of the inverse, I put minus a minus 1 times the derivative of a times a minus 1 times b plus a minus 1 times the derivative of b. Then I have a factor of a minus 1. So I take all the rest here. I take out this term. So the reduced gradient is called sometimes is the gradient of this. So this part, you should know it. You should know how to derive this. The difficult part is to derive this part. And then you have the derivative of y respect to j respect to y. You also need to know how to derive this. It depends on your function. And then you have this term here, times a minus 1. So I put the derivative of y respect to x here. Okay. So a minus 1 times b is y. So you already know. And this, let me call it p. It's a vector, and I will call it p. So with p equal to a times p is equal to this. Okay, and this is what is called the adjoint method. How large will be nu or p in this case? In comparison with x or with y, sorry.
The same size as y.
The same size as y, because it's a square matrix, so you have the same number of constraints and unknown here. So same size as y. So what do? You first solve, you give me an x. You solve your Navier-Stokes problem. You compute the gradient. You plug y and you have x. You have a vector. You solve the adjoint method problem, it's called. It's another PDE. This is a PDE, but this is another PDE. And it's the same PDE, but with a different right-hand side. So you have to solve your PDE twice. You have to solve your Navier-Stokes problem twice. Your elasticity problem twice. And then you can compute that joint. And then the gradient is any more than this derivative, you know it, times p, which is the joint variable, which is in fact a Lagrange multiplier, times this, that everything you have it. While you have it, the derivative of a you have it, the derivative of b you have it. Are explicit terms. Then you do a gradient method. This is a line search. You have the gradient. Give me a new x such that x minus alpha times gradient of j. And this is the joint method. Okay, so probably some of you work on that. You have heard of it. People here in CIMNE are working on this. You can see it in many places. And joint methods, what you have to do is to solve two PDEs. First one for the primal, y. Second for the dual, for p. And now you can interpret what is p. You know what is p. Now you know the value of P is a field as large as Y. So the displacements, you will have a P, and you will have a field that you can plot. What does it mean? Again, if I have the constraint, this equality constraint, this equilibrium, for example, if I remove the equilibrium in these points, will the cost change a lot or not? This will give you the value of P. P measures this. The adjoint has information. It's not only useful, it's not only a value that you have to compute, but it has also information.
You have something on chat.
Okay. How can we?
Question is there a transpose in step 2?
Or maybe. Yes, can be a transpose missed. Yes. Yes, probably. Yes. I took a symmetric A, but yes, typically it's a transpose. Okay. So you can interpret this adjoint method as this. Okay, I plug it here in more I did it, but I think it's too much. I think I will leave it to you if you are interested. You can have a look. But I wrote it here in discrete and in continuous form, because for me always was difficult to see. It's easy to explain here, but it was more difficult to explain it in continuous. So I put it the same colors just to see what are the same things. So Y here, it's an operator, it's a function. X, it's also a function. Here you see typical TD equation. Okay. But I put it here just for you for having it. So, and finally I have here also the algorithm. Okay. So when you have PD constraints, which is not the case in machine learning, sorry, it's not the case in machine learning what we have presented today, but on Friday we will see pins. Mohammed will come and explain it. And what they do is to minimize something with a PD constraint. And it's called physically informed neural networks, because physically informed means that you have PDs. Okay, and they do it differently. You will see how you deal with this constraint. Okay, the way you will deal with this constraint is you put it as a residual. Okay, but people who are working on PDEs and machine learning, sometimes the PD constraint you don't put it as a residual. You solve this adjoint method, and you have to solve this these two problems. That the only thing you need is that you have invertibility of the matrix A. Okay. Again, the line search is tricky and have the same problems as the other. Okay.
Another question.
Another question. Yes, can someone read it? The question?
Yep.
Yes.
In the case of, let's say, minimizing the drag, we don't know the functional form, right? We can compute the gradients using discrete values at different steps using, for example, finite difference.
Yes, I understand. He's asking, or she's asking, about this derivative here. Okay, so what is the partial derivative of the drag with respect to, for example, the shape of the cylinder? Okay, so sometimes you don't have it explicitly because it's not differentiable. If you want to do boundary is not differentiable, but then you can do different things, like for example, as here saying finite differences, or you can parameterize your domain with some variables, some discrete variables like norms or other things, or level sets, or you can regularize it with how is the name? I forgot. Phase field models, sorry, phase fields, for example. Also, you can use X as phase fields. So yes, one thing is by finite difference, but depends on the dimension of X. If X is too large, finite differences will be very expensive. but maybe you can parameterize your unknowns with a few variables, like for example, control points in NURBS or level sets in this case, or phase fields or whatever. But if you have PD constraints, the message is you have to solve these two equations: the primal, the constraint, the adjoint, and then with the adjoint you compute the gradient, and then you do a line search. Okay, so this is what you do with when you want to solve this problem of a cylinder, optimal cylinder in a Navier-Stokes, for example, problem. Okay. Questions?
Just me, where can I see some examples about computational mechanics? Some benchmark examples about optimization of computational mechanics. Which
Yes,
reference?
there is a book. It's not non-smooth mechanics for convex optimization or with convex optimization, something like this. Non-smooth mechanics, convex optimization. Sometimes it's called also variational inequalities. You can find it like this also. But yes, it's not a. There is not a lot because all you work in optimization and you work in mechanics. But there are people who are working on this. Yes, on both things. Yes. I didn't explain about this, like for example, the stresses of the duals of the strains and these kind of things also. But okay. So just to sum up what we have been doing today, we have had some interpretation of the Lagrange multipliers with Dirichlet boundary conditions, with contact problems, with the Stokes problems. We have seen what does it mean. We have seen also that eigenvalue problems, it's not only mechanics, also numerical methods are plenty of Lagrange multipliers. As we have seen, one example is eigenvalue problems. Plasticity, Schur complements. We have seen two algorithms only. I wish I had more time to explain you advanced optimization algorithms that are nowadays using it. For example, alternate direction ADMM, if you want to take a ADMM, alternate direction method of multipliers. Also, if you're interested in Nesterov acceleration, also proximal methods. These things are now used, very used in image processing. You can find them. You can find it in machine learning, of course, and you will find it also in mechanics. They are starting appearing in mechanics. We had here, in fact, a seminar in CIMNE speaking about contact problems with alternate direction method of multipliers 1 month ago. And then we have speaking about interior point methods. We have seen this central path and the boundaries. We have also seen the augmented Lagrangian, the interpretation of the penalty. What does it mean? It's also a line search for the dual. We have seen that depending on the value, you will take more importance to the primal of the dual, but you don't have to go to infinity. We have seen an interpretation in mechanics that is, in fact, like a spring with maths. And finally, we have seen this adjoint problem when we have PD constraint or optimal control optimization. Okay. So with this, we do. If you don't have any questions, or you do, no. Okay. So let's do the coffee break, and then we continue with supervised learning 2. Fechas que espera, primer para
Recording stopped.
Ha comentado Ricardo. ¿Qué pasa?